Hello everyone. So this is going to be our very last lesson. There was one other type of way to calculate volume by a shell method that we're just not going to get to. So I'm just making this the very last lesson. And instead of a quizzes by the end of this week, I'm going to give you guys, maybe even by Wednesday, a graded assignment over all the ways we've been calculating volume by cross sections and by revolving around a line here. So this lesson is going to be very similar to ones that we just started, except instead of revolving around the x or y axes, we are revolving around another horizontal or vertical line. So our examples are now going to look like this. We want to find the volume still of the solid form by revolving the region bounded by f of x is equal to 2 minus x squared and g of x is equal to 1 about y equals 1. So to revolve about y equals 1, just as we did with any x or y axis here, we reflect a portion of the graph over the line y equals 1. So at this point, go ahead and pause the video and get ready to graph either on graph paper or very neatly on notebook paper or any other kind that you have. And it's very important. Let's start with graphing the line y equals 1 and space out the units that we're going to label here to make the area that we're going to see easier to work with here. So if you noticed, I'm numbering here. Every 2 squares are counting as 1. All right, so we want to go ahead and I already drew in the line y equals 1. Let's go ahead and graph this as a parabola here. F of x equals 2 minus x squared, y-intercept at 2. And if I count over 1 and down 1, I'm already intersecting the line y equals 1. So that's really all of the part of the parabola I need to show. And then this is going to reflect down here as well. All right, so this is the area, the shaded region right here. That's going to start to get revolved, so it's actually going to show up as this entire section. And then as it revolves, we get that circular motion here, and we start to see something that looks like this. So with these problems, we're either going to encounter slices that are solid circles or that we call disc, or washers where they have that opening in the middle here. So if you take a look at each slice, each circular slice, they're a disc. They're solid. There's no gap in the middle. So this is what we're looking at. So each slice, we'll say, is a disc. Then we want to write out the radius first before we get to area. So the way I'm going to sort of go through the steps to setting this up is we first need to write out an expression for the radius of each slice, and then the area, and then that leads us to the volume. So the radius of each slice, I'm going to start right at the center here. In this case, is the line y equals 1. Now, I'm actually going to go back down to the x-axis. It's going to be a lot easier. It's going to tie into the ways that we were looking at area bounded by curves before. I always want to go, if it's with respect to x, the top curve minus the bottom curve. So technically, I could go all the way just down to this curve right here. Now, the curve that got reflected in this case, most of the time I don't do this, but in this case, it's a lot easier. So this curve right here is very easy to write out the equation to. This is just y equals x squared. So the radius is going to be the distance between this 1 and this x squared, so it's just going to be 1 minus x squared. So then the area of each slice, which is pi r squared, is going to be pi times the quantity 1 minus x squared squared. And then our volume, first write it, we could put the pi on the outside. We're going to eventually do that anyway, so it's going to be pi times the integral. Now, in this case, we could go from -1 to 1, and we wouldn't need to do anything else. But because this is symmetric here, I'm going to go ahead and go from 0 to 1. So that means I'm actually going to double this because I'm using symmetry here. So I'm going to have the 2 pi on the outside because I'm just going to go from 0 to 1, but then I need to double that to get this volume. And then it's going to be the quantity 1 minus x squared squared dx. Now, there's no need for u substitution here. You could do it. But it's a lot easier if we just expand this quantity. So we'll have 2 pi times the integral 0 to 1 of 1 minus 2x squared plus x to the 4th dx. Take the antiderivative now. So we'll have x minus 2 x cubed over 3 plus x to the 5th over 5 from 0 to 1. Substituting in the 1, we'll get a 1 minus a 2/3 plus a 1/5, and then really just a minus 0 after that. Getting common denominators. So when I ask you guys to evaluate by hand on the graded assignment, this is what I'm going to want to see. Let's get everything with 15ths here. So we'll say 15 15ths minus 10 15ths plus 3 15ths. So combining all of these, we're going to get 8 15ths times 2. We're going to get 16 pi 15ths cubic units. All right, but again, just going back to the picture, this one was a little bit easier. Washers are a little tougher to work with because you have to do some subtracting for the area as well as the volume. All right, so looking at a second example, we want to find the volume of the solid form by revolving the region bounded by f of x is equal to x cubed and the lines x equals 0, y equals 1, about the line y equals 2. So go ahead and start a new graph, pause the video, draw the line in of y equals 2. But we also want to draw on the lines x equals 0 and y equals 1. So there's our vertical line, x equals 0, just the y-axis, and then y equals 1. Now, since I'm going to be revolving this about y equals 2, I actually want to reflect the line y equals 1 up here as well. We want to get perfect symmetry with what we're drawing here. So everything we draw, I'm going to get reflected over this line y equals 2. All right, so as I go to draw in y equals x cubed, so I'm looking here between 0, x equals 0, and y equals 1. So we're looking here to here, and we know what the line or the curve is going to look like here. So imagine that it's coming up from here, it curves, it's concave down, and it turns to concave up. So this is a part I want to reflect. So notice where it stands with respect to y equals 2. This point is 2 units below, so the point up here is going to be 2 units above, and then we copy it here. So there's the reflection over the line y equals 2. All right, so this is the portion that gets shaded. Likewise, it'll be shaded up here. And we start to spin this, so we're going to get our circular slices here. But because there's an opening in the middle, each slice is going to be a washer. So I'm just going to start in the middle to show that opening the easiest way. So there's our outer circle, and then our inner circle is like right here. And then the same thing is happening here. Just kind of draw that in the middle. On the outside as well. All right, so here we want to be very careful with each radius. I'll just say radius of the outside. And we need to represent the radius of the inside circle. All right, so the radius of the outside, again, I'm going to start with a 2 and go down to the bottom here because that was where our original curve is. In the last problem, that was a little bit easier to write out than the curve we were already given. Here, I'm going back down to the original curve. So I'm going to do this in red here. So if I started right here at the center and I go down to this curve, again, it's top minus bottom. So this is 2 minus that curve x cubed. So my outside, the radius of my outer circle is going to be a 2 minus x cubed. And then, let me see, I'll try purple here. And then the radius of the inner circle is going to start at the 2 and just go down to the 1. So it's going to be 2 minus 1, or just 1. So then my area of the outside, or outer circle, is going to be pi times my radius squared. And then the area of the inner circle is going to be pi times 1 squared, which is just pi. So now my volume, there's no symmetry to worry about here. I'm just going from 0 to 1. Put the pi, actually I'm going to put the pi on the inside here for a second. So this is going to be the volume is going to equal, let's say 0 to 1 of pi times the quantity 2 minus x cubed squared minus just pi, and then we'll have dx. Now here, if we took the pi out, we have to take the pi out from both of these. So I could say we'll put the pi on the outside. It's going to be integral 0 to 1. I'm going to go ahead and expand this quantity right here. So we're going to get a 4 minus 4x cubed plus x to the 6. Now, because I took the pi out of both of these, this is just going to be a minus 1 at the end. We can combine the 4 and the 1. So the integral from 0 to 1, we'll just get 3 minus 4x cubed plus x to the 6th. So now the volume. And again, because we have pi's with both of these, not to get confused, I'm going to treat them separately. So we're going to say is the integral, remember this is going from y equals 0 to y equals 1 of pi. I'm going to write this as y to the 1/3 plus 1 squared, and then just minus pi, and then it's dy. So now if I were to take the pi out of each one, again from 0 to 1, I'm going to go ahead and expand this. So I'm going to get y to the 2/3 plus 2y to the 1/3 plus 1, and then minus 1, because I factored out the pi from that part. Dy. Now we'll take the antiderivative. So we're going to get y to the 5/3 divided by 5/3, so it's going to become 3/5 y to the 5/3, and this will become 2y to the 4/3 times 3/4. So I'll write this out. It's going to become 2 times 3/4 times y to the 4/3, and then those ones cancel out, and we're going from 0 to 1. So I'll simplify this as I evaluate. So this will just become 3/5 times 1 to the 5/3, so we're just going to get 3/5. This will actually become 3/2 times 1 to the 4/3, so just 3/2, and then really just minus 0. Getting common denominators here of 10, so we'll get 6/10 plus 15/10, and we'll get 21 pi over 10 cubic units. All right, guys, so our very last examples for the year. The worksheet I'm going to give you, I'm only giving you 2 problems off of here to do. So I'm calling this, it's a GIF 7-3, but it's called the other types of problems. So just 2 part B and number 7, please evaluate all integrals by hand. I have this on the next page. So again, it's volumes of revolution about lines other than the x and y axes. So I call it GIF 7-3 other. So I'll scroll down, but also make a PDF of this as well. But you could pause the video at this point right here. So just do number 2 part B and then number 7.